In this section, we will discuss really important aspects of multi-thread programming. In particular, we will discuss locks and how we can use them in order to protect critical section. Then we will see how we can implement locks in Python. Some guidelines, some recommendation on how to organize the code will be part of this lecture. Have fun! Let's see how we can solve the critical section problem with locks. Well, the lock mechanism is the simplest synchronization mechanism. Imagine that we have a special kind of variable, the lock variable. The lock variable can have two possible values. It can be either 0 or 1. If the lock is 0, then the critical section is vacant, so a thread can enter in the critical section and access the results. But when he enters, it should lock the door so that others cannot enter in the critical section while it's occupied. And in locking the lock, you set the variable to 1. Clear enough. Also, the access to the lock would be in a critical section. So, how can we solve the problem? Well, the downstanding hardware provides us special atomic operation that make it possible for us to avoid critical section for this simple variable. Basically, this special atomic operation cannot be interrupted, and not even interrupt can interrupt their execution. So we are sure that there's no issue in accessing the lock itself. Let's see how things work with a simple animation on the right-hand side of this slide. First of all, we have a thread T0, and the thread checks whether the lock is open or is closed. The lock is open, and the value of the lock variable is 0. The thread can therefore enter the critical section and set the lock to 1, so close the lock. Now, let's assume that another thread wants to access the critical section. Well, the new thread, the thread T1, checks the lock, and basically the lock is set to 1, so it's not possible for the thread to enter the critical section. Basically, the thread T1 cannot enter the critical section until the thread T0 releases the lock by setting its value to 0 and leaves the critical section. How does the lock work? Well, we said before, actual implementation of locks requires special operation and support from the operating system. In the following, we would like to just give an idea of the model of the lock. So it's not a real implementation. I want to stress this thing. Well, first of all, we have to consider two main operations for a lock: the acquire operation and the release operation. Let's start by considering the acquire operation on the lock. Basically, when a thread wants to acquire the lock, it must check whether it's actually open or closed. So, if the lock is currently locked. So if it is closed, the thread has to wait, keeps on waiting if it is blocked on the lock. Otherwise, if the lock is open, the thread can acquire the lock and set the lock state to 1, so it can actually lock the lock so nobody else is able to enter in its critical section. So everyone trying to acquire the lock gets blocked. The second operation is release. When we are releasing a lock, we simply set the lock state to 0. So basically we open the lock, and by releasing the lock, we let the next thread to acquire the lock enter into the critical section, do whatever it has to, and then release the lock. It's clear one thing. Now we have to explicitly handle this synchronization issue. So in our application, we not only have to consider the business logic, but also we have to consider some synchronization logic. This makes programming more complicated and forces developers to consider the mechanics of multi-threading. And that's one of the reasons why multi-threading is a complex task that sometimes causes problems in modern programming. Let's have a look how Python implements lock. In particular, the threading module provides developers with lock class. Lock implements the primitive lock object, and this object is very easy to use. Provides you few methods to interact with the lock, acquire and release. Let's consider the acquire method. We can have different ways to use acquire, blocking and non-blocking. Let's consider blocking acquire. Well, with acquire, you attempt at acquiring log. So if the lock is open, no problem. The thread actually acquires the lock. If the lock was already acquired by another thread and the acquire is blocking, the second thread attempting at acquiring the lock is blocked for an indefinite amount of time, as long as the other thread is keeping the lock. Okay? On the contrary, when the acquire is invoked with the blocking set to false, we may specify a timeout, and the thread is blocked at most for as long as the timeout method specifies. Have a look on Python documentation for more details. However, the message is, the acquire method is the method you want to use to acquire a lock. You may have blocking and non-blocking semantics, okay? More often than not, you use blocking semantic. It's the semantic we discussed so far, and it's very, very important. Another important method of the lock class is the release method. The result of release is very, very simple. It simply releases the lock, the associated lock. this can be called from any thread, not only by the thread that actually acquired the lock. When the lock is locked and you invoke the release method, the lock is unlocked and the method returns. If any thread is blocked on the lock, well, the method allows exactly one of them to proceed and enter the critical session. That's why it's very important. So again, we need to use this method, acquire and release the lock, to manage the access to critical section. And we are asking programmers to include in their application not only the business logic, but also the thread management and thread synchronization logic. Another method that can be useful for the implementation of complex synchronization is the locked method. Well, the method returns true if the lock is acquired. So you don't need to have your thread attempting at acquiring a lock that is already locked by another thread. So you maybe don't want this. And in this case, you can use the lock method to query the lock and ask if it was already taken by somebody else, by some other thread. And you can adapt your thread synchronization logic accordingly. This may make sense or not. Of course, when you start implementing this type of optimization, the code is getting or will probably become very, very complex. So think twice when you want to use this type of construct. Now we have a better understanding what locks are. We understand how we can use locks in our Python application. So we have an idea of the lock object, how we can use them, and how we can take advantage of the acquire and release method. Very simple. So let's try to understand how we can solve the critical section issues through locks. Well, this is an example. Here we have a couple of threads, thread 1 and thread 2, and we have the lock L, and the lock L is an unlocked state. So we start the execution, and the program counter, of the thread is indicated with a magenta arrow. We see in this animation that thread 1 acquires the lock, and by invoking the acquire method of the lock L, it sets it to its lock state. How can we do this? Well, lock is a shared object among thread 1 and thread 2. Once the lock has been acquired, thread 1 can enter its critical section and can operate on other shared resources, other shared variables that are protected by the lock. Now the operating system schedules thread 2, and thread 2 attempts at acquiring the lock. Unfortunately, for thread 2, the lock has been acquired before by thread 1, and as a consequence, thread 2 is blocked, is execution state moves to blocking state. So you have a transition from running thread to blocked thread, and the thread is blocked on the lock that it attempted at acquiring. Well, thread 2 is there and is there waiting for thread 1 to release the lock. Once thread 1 releases the lock object makes it possible for thread 2 to actually attempt acquiring the lock again. So thread 1 can now leave the critical section and thread 2 can enter finally. Now thread 2 can access the critical section and can gain access and interact with the resources that are protected by the lock and are allocated into the critical section. It can have exclusive access to these resources as long as it's running into the critical section. And it can operate into the critical section till it leaves. And to leave the critical section, remember, you have to release the lock so that the other threads are enabled to enter into the critical section. What happened if a programmer forgets to release a critical section? Simple. It's a problem. It's a bug. It's a bug because just one thread can enter into the section and it stays there basically forever. So no other thread is enabled to enter into the critical section and operate on the resources. This means that we have a problem. We have a synchronization bug. We have an issue. Now it's time to have our hands dirty with some Python code, and it's time to actually test what we have learned so far. Well, the example is quite simple. We have a multi-threading application where we have two threads, and these two threads are attempting at incrementing the value of a shared variable. That's the idea. So let's get into the details of this code. First of all, let's consider the main. In the main, we have a quite familiar now structure of the code. Basically, we have two threads, thread T1 and T2, and thread T1 and T2 are created by passing in the myThread function. Plus, we pass an argument C, which is a counter. It's an object. It's the shared memory that we will use for the coordination, for the interaction amongst the threads. Then, as usual, we will start thread and wait for their termination with the join. So very, very familiar code now. And here, the definition of the business logic of threads. We have our familiar myThread function that takes in an argument, the counter object. We will see later how it's defined, and basically every thread runs a for loop with 5 iterations, and for each iteration it increments the counter and sleeps for sometimes between 1 and 2 seconds. And then here we have the counter class. The counter class is the the class that implements the shared resource among the threads. Let's zoom in to read better. This is the counter class. Now we can read better. So zooming in is useful. We have a constructor where we have a value as an argument. The default value is 0 if we don't specify anything. And we define a couple of attributes. We define a lock, which is an attribute, and a resource, the resource value, and the resource is the actual resource the threads are competing to acquire. So we need to protect it. Then we have the increment method. Well, in the increment method, what happens? Simple. We provide threads access to the shared resource. So this method is a critical section. And so we need to protect the critical section and access to shared resources. So what we said before, easy, we need to protect shared resources with a lock. So we have lock acquire, and this makes it possible to guarantee that a single thread can be executing into the critical section, whereas all other may be waiting or executing somewhere else. The thread which is executing into the critical section can access the resource, and in this case the operation is trivial. We simply increment the value of a variable, of an attribute. It's very simple. We print something on the screen, and important, we release the lock. This is extremely important. We said it before. If we forget to release the lock, it's a problem, because no other thread will be allowed to enter into the critical section. So it will be a problem. Let me stress another important thing. The idea of using object-oriented design and in order to define classes that embed the resources, and somehow the logic that rules the access to these resources is a good way to organize your code. So please follow this idea. Use object orientation and try to use the thread synchronization logic within these classes. We will see how we should organize even complex thread management strategies in this way through the use of monitors. But we will see it in future lectures. But please keep in mind that this is a good design approach. Now, well, we want to improve the design of our class. So let's consider the idea of handling exception. In this case, the code is trivial, but I want to show you a pattern that you can reuse in your own class design. That's the idea. You can basically acquire the lock and then attempt at catching exception, and don't forget to release the lock. And in order to avoid problems in case of exception, the lock release logic should be within the finally clause. So that's very important. So please follow this pattern. However, for the ones who know something more about Python, you know that you can use the with statement. Basically, this code implements the same logic that we have implemented with the try and final. As simple as that. This is a pattern you can use and reuse in your application. So don't forget it. Now we can run our application as usual with the console, and what we see that thread1 acquires the log, and the current value of the value attribute is 1. Then thread1 release the lock, and thread2 can acquire it, and so on and so forth. So both the threads are interleaving their execution in this simple, very simple application. It is what we expected. So far, we assume that different threads attempt at acquiring a lock. It makes sense in the beginning, is what you think. But what if a thread that acquired the lock attempts at acquiring the same lock again? Well, the situation is tricky, and in particular, what happens is not nice. Basically, the thread first obtained access to the log, so access to the critical section. The second time it attempts at acquiring the lock is already acquired. So the thread is blocked and stay there forever. And nobody else is able to unlock the lock. So nobody is able to enter into the critical section. And this is a problem. It may happen for several reasons, but sometimes it happens. So we need some solution for these situations. The solution is reentrant locks or locks. Basically, a reentrant lock works as an ordinary lock, but has some special feature. Basically, a reentrant lock makes it possible for a thread to acquire the same reentrant lock multiple times. So it works exactly like another lock, but when a lock acquires multiplicity of time the same lock, it does not block. So your application is not stuck. If you look at the code on the right hand side of the slide, you see that you can define the rlock with the rlock class, which is implemented into the threading module. You can acquire the rlock 1, 2, 3 n times, as many times as you want, and you don't get stuck. So you don't block if you acquire a multiplicity of time the same lock. And you have to release the lock, but you have to release the same number of time it was acquired. So the rlock must be released. If you acquire the rlock 3 times, you need to release it 3 times. If you acquire the rlock 10 times, you have to release it 10 times. Otherwise, nobody else is able to enter into the critical section. So this mechanism helps a lot in the development of multi-threading application, but still requires some care in its use. Well, in this section we discuss a lot of issues. We started by introducing the model of lock, a basic idea that's implemented in the major language out there, not only in Python, and how log can be used in order to protect critical section and to guarantee, therefore, that a single thread is executing into the critical section at any time, which is a very, very important thing if we want to have control of our software. It's very important. Without this, we cannot have thread-safe software. So it's really a basic concept everyone is expected to master. Okay? Then we studied locks in Python, and we introduced rlocks, reentrant locks. They have the same interface. They work the same way. The only difference is that reentrant lock enable a thread to acquire the same lock a multiplicity of time. It's something that's useful. It's less efficient, slightly less efficient than locks, but it's a necessary tool for the implementation of multi-threading applications. Finally, we have had our hands dirty with some example to understand how to use locks in Python to actually protect critical section. And a strong message. The idea is please organize your code so that you have threads, so active entities, and resources, passive entities that are organized in terms of object. Why? Because object makes it possible to encapsulate a number of aspects that should be considered in the implementation of a resource. The way you implement the resource, the way you represent the resource, and important for our purposes, the way you synchronize the access to the resource. Everything encapsulated, hidden within a class, can make your software quite easy to manage and maintain in the time. So, strong recommendation. Follow object-oriented approaches.